I'm Jackie Yang from Stanford University, and this is the work I've been done last year when I was an intern at HP. So on behalf of my co-authors, Hiroshi, Horii, Alexander Thayer, and Tico Ballagas, who should be here today, and I present VR grabbers using ungrounded haptic retargeting to provide passive haptic feedback for grabbing tools. Okay, so everyone here, so we all believe virtual reality is really important. It's good for training and simulation purposes. And we all believe that to provide a realistic experience, we need haptic feedback for it. And however, traditionally, providing haptic feedback requires hardware with precise actuators. They add complexity to the system, basically. And of course, illusion-based technique like haptic retargeting shows great promises by offering haptic feedback without adding actuators. One common strategy is using passive haptic prop. For like in this case, there's only one real cube on the real desk, but the system tricked the user to think that they are manipulating multiple cubes in virtual reality. However, this does not apply to tools and requires many different haptic props for objects of different shapes and sizes. So our problem is, how do we apply haptic illusion-based technique onto grabbing tools? So in this paper, we focus on a specific type of grabbing tools, specific type of handheld tools called grabbing tools. And those kind of tools usually have two handles, and then is used to grab object, including tweezers, pilers, and chopsticks. Of course, some other tools, although they are not grabbing tools, but they share some similar characteristic as grabbing tools, for like scissors, snips, and wire strippers. They also have two handles, and then the majority of force feedback while operating the tool is between two of the handles, so therefore ungrounded. And our technique can also be used to represent part of the force feedback for them. Okay, so we introduced this controller called VR grabbers, which is, you guys can pass around and check out. So this is without the white tracker on it, but it's similar. So this VR grabber has a similar shape with training chopsticks, but it's pure passive. And to provide a haptic feedback for VR grabbers, we created this technique called ungrounded haptic retargeting. It leverages the visual dominance or visual perception to create a haptic illusion where the virtual object feels physically present. So as you can see in the video, in virtual reality, it appears that the controller arm is converging on a virtual object, but in real life, the controller is just converging with each other. So this technique leverages the ungrounded feedback inherent in grabbing tools. The user attributes the force of the opposing arm to the force that they're expecting from the virtual object in between their the virtual object that is in between the virtual controller in the virtual environment. So we'll basically achieve this by dynamically adjusting the converging rate of the controller arm in virtual reality. So now we can go to details about the system. So what's so special about this ungrounded haptic retargeting technology? So the first thing is our technology can accommodate object with different shape and sizes. As you can see, the user can grab an object, sometimes a cubical object, sometimes a spherical object. They have different shape and sizes, but the technique can always accommodate for all of them. Also, it can adapt to users' change of intents. The user may close their controller completely sometimes, and then they also may want to grab on some object sometimes. And in extreme cases, the user may also close their controller halfway through on an object, then they change their mind, and then they go somewhere else, and then to close their controller completely. And none of those interactions is scripted. So we don't have to ask the user to pick up a specific controller. They can use this controller to explore an interactive environment. So to solve those few characteristics of ungrounded haptic retargeting, we introduced this algorithm called key state mapping, where we define three concepts. The first concept called state, which is the opening angle of the controller in both physical world and virtual world. In this case, as you can see, this is where it looks like in the virtual world. This is the exact opening angle of the controller, whereas in the real world, it's closed 50%. And key state is a field state that's defined by the tool controller that is necessary to maintain the illusion. So like in this case, two key states are defined. One is closed, the other is opened. As stated in the name, open means when the controller is completely open, and the controller should be both completely open in virtual reality and in reality to maintain the illusion. Whereas when the controller is completely closed in the real life, it should be just on the edge of the object in virtual reality to provide those kind of force feedback. So then this is the kind of interesting part where we basically generate all the other state, which we call transfer state, according to the current state and the key state. So like in this case, if the user closes their controller 25% more, then they should be reached at this specific transfer state. And if they open their controller 25% more in real life, you should reach this specific transfer state. This basically says if this object becomes larger or smaller, what will happen is just the rate the user's controller converge in the virtual reality will change to represent the force feedback. So no haptics, no active haptics is required, but we can emulate different object shape and sizes. So now let's talk about change of intent. What if the user then move away and then the object's no longer in between their controller? So we can do the same thing. We generate a key state, and note that because there's no longer an object, the closed key state changes from on the edge of the object to completely closed. So with this, we can just generate a transfer state similar as before, and what we will have is basically if the user opens the chopstick, it will behave exactly the same as before, but only when the user is closing their chopsticks, their virtual chopsticks will move a little bit faster than real life, so that when they completely close it, it's also completely closed in the real life. Sorry, it's also completely closed in the virtual world to represent the force feedback of completely closed controller. For more details, please see our paper. Okay, let's talk about implementation of this. So this is the VR grabber controller which we are passing around. I didn't attach the VR tracker today, but that is used to track the position and orientation of the controller in virtual reality and in real life. A potentiometer is attached to track the opening angle of the tool in real world, so that we can represent some transferred version of it in real life, in the virtual world. And as all the grabbing tools, we have two handles and one joint. On the right, we show the dimension of this controller. So basically, the handle is around 11 centimeters, while the maximum opening angle is around 30 degrees. Note that we have this special haptic block over here. I'll talk about this usage later, but we put it there so we can limit the minimum opening angle. So like when they close the controller, we can adjust in a 5-degree granularity. It means that we can make the controller close at 1 degree, 6 degree, and 11 degree, and so on. Okay, so the first study we conducted is to explore the limit of the illusion, basically how much we can slow down and speed up the handle. We basically use that haptic block, and then we have basically 5 positions of that haptic block. And we put the haptic block in a specific position in both virtual reality and in reality. Because we have 5 positions, we have like total of number of 25 configuration. Each user try those 25 configuration in a random order. And in each one of the trial, we ask user whether they notice there is any retargeting, which means that whether do they feel like they are holding a different controller in real life than in virtual reality. Yeah, so this is what the user is doing. So the user basically closes their controller multiple times, and then we ask the question whether do they feel like there is any retargeting happening. And the result is we use this detection threshold matrix, which essentially means 50% of the people think there is some retargeting happening. And the result is we can change the control display ratio in the range of 0.71 to 1.77 times. What does that mean? That basically means that if this is the controller, if the two blue state is basically the completely closed state and the completely open state, if the user moves halfway from the open state to the closed state, we can render the virtual chopsticks either in the 0.7x motion or 1.77x times the original motion, like showed in those red boxes. Okay, so then we think a little bit more. We don't necessarily have to make the tool completely closed in the real life to represent the closed chopsticks, right? Our goal is, as you can see in the previous slides, this technique works both in the positive state. We can speed up users' closing of the chopsticks, or we can slow down users' closing of chopsticks. So we think that we don't have to make the user completely close the chopsticks. We can put the block in a specific position where we can emulate the largest object possible, while when the user closes their chopsticks, they can still feel like their chopsticks is closed. So we decided to put the haptic block in position 2, where we can emulate virtual object size almost less than 3 centimeters. And for the next study, we measure the task performance and gather users' feedback. So one problem is we need to implement a VR grabber without ungrounded haptic retargeting. The way we implement that is inspired by prior work and common approaches in state-of-the-art VR games. We do that by make the virtual opening angle and the real opening angle always the same until they actually grab on an object. And after they grab on the object, the opening angle no longer changes, so that the handle stays on the surface of the object. Where at this state, the two controller hasn't converged yet, so you can still move your controller around, while the virtual opening angle will no longer change. So we designed this task where the user first align their controller with the virtual controller to start a timer, and then they pick up a movable cube. They align this movable cube to a target cube. And once they release in the correct position and orientation, that's when the task ends. Which we ask the user to try those two configurations in a balanced order within subjects. For each configuration, we ask user to try 36 performance tasks, as I have said before, and the object will be rendered in different sizes, and we will ask them to do different movements. And after each configuration, we ask user to fill in this presence questionnaire. So the result of this study basically shows that the controller with ungrounded haptic retargeting can reduce the task completion time, basically increase the performance by almost 2 seconds. And in the presence questionnaire, we also show higher realism. Okay, so what's the limitation of this technique? So currently, we only implement ungrounded haptic retargeting with the single controller VR grabber. And the other limitation is currently the controller can only work for objects smaller than 2.95 centimeters. So in the future, we could either apply this similar technique to other controllers other than just VR grabbers. We can, of course, apply them to grabbing tools. We are pretty confident about that. We can even apply those to this specific controller, which is called a Wolverine by Choi et al., which is basically they have an active brake on each one of your finger, so that if you grab a virtual object, you will stop your finger at where your finger touches the virtual object. We could potentially implement a passive version of that. Basically, your finger always stops at the same position, and we use ungrounded haptic retargeting to make you feel like you're holding object of different shape and sizes. On the right, we can, the other future work could be we can use some active mechanism to increase the working range of this tool. So for on the right, we show one of the design mentioned in Twitter's device. This design basically is really effective, really cheap, but the only problem is it can only stop at discrete point. And also it has a lot of braking force, which is ideal for simulating hard object. And because it can only stop at a discrete point, we can potentially use ungrounded haptic retargeting to fill in the gaps. Basically, the controller stops at the nearest point, and then we use ungrounded haptic retargeting to emulate the differences. So that basically we can emulate objects with larger sizes. So what's the takeaway of this talk? So we think in the future, every consumer do not need to wear expensive haptic equipment or prepare a variety of haptic props to have a realistic haptic experience. With ungrounded haptic retargeting, everyone can enjoy quality haptics at a lower cost. Thanks. I'm happy to take any questions.
Thank you, Jackie. Any questions? All right. Me again. So during your summer internship with us at Microsoft Research, you got a chance to try our various controllers, normal touch, the claw, and so on, which allow you to grab virtual objects. And of course, we do this actively by breaking your fingers down, or breaking them, right, and acquiring the objects. And I'm wondering, did you iterate through the various controllers, or did you start with chopsticks right away? Because the one component that you didn't really talk about is sort of the extension of the chopsticks, right? How long are they? How close are they to your finger? I mean, you touched a little bit on that in the future work part, talking about Wolverine, right? Could you integrate this totally in your fingers and just do that? Or is there an effect of the length of the chopsticks?
The reason why we focus on chopstick initially is we want to implement a controller that can basically manipulate virtual object easily in virtual reality. We consider about pilers and then tweezers, but usually they have a very limited working range, whereas chopsticks usually have a larger opening angle than them. And as for extending for like maybe longer handle chopsticks or shorter handle chopsticks, we try to, when we measure our limitation, we always try to measure the control display ratio, which we believe is like a little bit more generalizable. So you can imagine if you have a longer handle chopsticks, you can still apply the similar control display ratio like this measurement for like if you are completely open chopsticks. Right now it's around 5 centimeters. If the completely open chopsticks is 10 centimeters, you could potentially emulate a 6 centimeters object. That's what we imagine.
Okay, cool. One more question. If not, we're going to thank Jackie again. And it was a perfect segue.